Okay, we're going to look at problem 22.1 mostly because I want to go through kind of quickly, make sure we're all on the same page with using these functions moving forward. Okay, so big picture, what we're doing is we're coming up with functions that solve differential equations. And so on just on a high level, is what it means to solve a differential equation. For what we are doing now, we're going to be given a differential equation, something like this right here. This dy dt is equal to this, equation yt cubed minus 1.5y. So the reason why it matters is because we need to come up with, so like this symbolic way, we're going to come up with another equation, right? We're going to have some y is some function of t. But usually when we're going to solve a differential equation numerically, so using the Euler's, midpoint, Hume's, RK methods, what that means is that we're going to come up with for any given point for any given point t, what is the y value at that point? So that's the numerical process. So, but first, let's do it symbolically. And the symbolically we have, we're going to use dsol. So it's a built-in thing to MATLAB. So I have over here in MATLAB, I started this up. I have problem 22.1, cleared my memory. Here is the equation right here, so the symbolic. So how do we do it symbolically? Well, the first thing we need to create the symbolic variables. So I'm going to sims t and y of t. And I'm going to say that my y symbolic is dsol of, and then if I'm going, the old school way would be to do dy equals, but I'm not going to do that. I'm actually going to try to stick with the current method. It's going to be diff of y, so it's the derivative of y equals, since inside here you have to do the double equals, so that's equal to y times t cubed minus 1.5 times y. So I can run that, that'll work, but then when I run that, you'll see I'll get like this constant in here because I'm not using my initial conditions. And remember, this is an initial condition differential equation, and that initial condition is given right here, that y of 0 is 1. So I'm going to put that in here for my initial conditions. Y of 0 equals 1. Again, when I'm doing it this way, you have to have the double equal sign for all these things. Run that, and boom, there's my equation. So, okay, yay, I have an equation. I'm going to say that for what I'm doing, that's not terribly helpful because I'm going to be comparing this to the Euler's and midpoints and stuff like that. So I'm kind of going to use this as my truth, but I want to be able to plot it because I'm not going to be able to look at the equation and say that's what the other ones give me. So to plot it, there's lots of different ways in MATLAB. Something I've picked up on lately is fplot, and to fplot y sim, and I can do it from, the problem asks from 0 to 2, right? So I can go from 0 to 2. And then I'm going to plot that, grid on, zoom on, hold on, box on. That's just how I like to do my plots. Boom, and now we should have a lovely plot. There we go. There is our plot. So that is what it's our symbolic answer, but it's what we're going to kind of reference as truth from here on out. Okay, so now we're going to start doing the ones that are interesting. So this one is purely just to help us like have a reference point. How are we doing? So now we're going to start doing this. So first off, Euler's method. We're going to create an Euler's method function to solve this problem. So the way I'm going to do this first time I'll just do it how I would normally do it, and then we'll kind of get a little more efficient. So if I want to do Euler's method, the way I usually create a function is I write it in a script first, and then I functionalize it. I go through and I make it a function. But so let's do that. So in general, what we're going to have is we're always going to say for I equals 1 to length of t in this case minus 1, because at any point in time we know at t equals 0, y is equal to 1. And then we're going to go through for every value of t and get another thing. So we're going to do this with an h of 0.5 and a 0.25. So at first, let's just come in here and I can say h is equal to 0.25. And I'm going to say, so therefore t equals 0 in steps of h to the 2, right? That's what's given in the problem. And my initial value, y, is 1. So now I could do this. Now I cannot do that. So mathematically, that kind of makes sense to say y of 0 is equal to 1. But remember, in MATLAB, that's saying the 0th element of the y vector. And MATLAB does not like 0th elements because it starts at 1 like normal people instead of C and C++ in Java. So we're going to go with y of 1. So now that will say y of 1 is equal to 1, which is lovely, but I am going to go like that. And the reason being, it's a little bit of a just, if you do y of 1, if you run it and then you still have like some memories in there, and then you do it again with, say, you fix it, it'll only replace the first element. If I have a vector y in there and I put a value of 1, then it wipes out the vector and it starts over and it makes it all 1. So it just makes life easier. And actually, quite frankly, this will probably help deal with this symbolic stuff. But also, to help us deal with the symbolic stuff, let's just go ahead and clear y and t so that doesn't cause us problems. Okay, so now for here, and Euler's method is always what? It's my y of I plus 1, so my next value, right? So we're first pass through the loop. When I is equal to 1, I already know that y of 1, the first one, is equal to 1. So I want to find the second one. That's always equal to the y of I plus the slope times the step size. That is what Euler's method is. That is what, and quite frankly, it turns out that's what midpoint and Hume's method, that's what all these methods are. So that's what they are at their core. So the question is, we need to figure out some stuff. What is the slope? Well, the slope is, we're given right here. This equation is the derivative of y, which is also known as the slope, right? So I need to create a function. I can say dy dt is equal to at ty, right? So, and now I could do this y comma t, but it turns out that once you start using the built-in functions, it always wants the independent followed by the dependent. And since I'm writing this, I can do it any way I want, so I might as well just be consistent. And so this is y times t cubed minus 1.5 times y. Okay, so that is my function dy dt. So this is all kind of set up, right? I'm choosing to solve it with a step size of 0.25. I am solving it in the range from 0 to 2 in that step size. My initial condition is y is at t equals at the first element of t. So remember that y is 0 is the first element of t is 1. Okay, and then here is my function for throughout all this. And so what I'm going to do is I'm going to replace the slope. What is the slope? Well, the slope is simply dy dt at t of I comma y of I. And that is Euler's method. It's just that simple. And so hopefully I didn't make any mistakes. Let's plot this up. I'm going to plot now my t against my y. And since this is Euler's method, I can do this with, I don't know, I'm going to do a red stars and a dashed line. Okay, let's run that, see what it looks like. See if I made any mistakes. Nope. Okay, that looks good. So that is my Euler's method. So it's not terribly accurate. As this changes quickly, we start to get pretty bad through there. If we, just for giggles, if we did this with a step size of 0.5, it's just going to get worse, right? We're going to really start to miss what's happening. So there, that's pretty horrible. But honestly, a step size of 0.5, that's a pretty foolish step size. If I do, say, 0.05, then we're going to get into, you'll see it gets more accurate. You know, like the finer the step size, the closer you can track it. But to be consistent with this, we're going to do this. Okay, so that's lovely, but that's not exactly what was asked. And so now, so that is the Euler's method. That works lovely. It's a lovely Euler's method, but let's go through and actually make it a function. And so I have a little spot right here to make it a function. Yay, look at me. So what are we going to do? I'm going to take, this is really the bulk of the function, and I'm going to copy and paste it right here. So we got to do function Euler of, and actually we have to say the output, right? So y equals, if I can spell, y equals Euler of, and I don't know, and it's, what am I sending it? I am sending it my, do I decide here what I want to send it? Create a function, blah, blah, blah. Okay, so I need to figure out what to send it. And so I need to send it my function, dy dt, and I need to send it my independent variable, t, and my initial condition, y, I can call it y naught. Okay? Now, here's the deal. You'll notice I am not sending it h. Please, please, please. Of course, I wouldn't do this, but I have maybe heard of, say, friends that I worked with that had the same job as me in the same seat and everything. You get bit when you do stuff like this, because what's going to end up happening is if you're going to change it one place, so if I come in here, I'm going to set it change it to, oh, I need to do this with 0.1. Okay. And then you're going to, and it'll take care of some stuff. It's going to make it a mismatch. So what I'm going to do is I'm going to send it my function, my independent vector, and my initial condition. And then right off the bat, I'm going to say h is equal to t2 minus t1. So I'm going to calculate h right here. Because if you, again, if I didn't ever mess up, I could send it h and I could say h is equal to 0.25 or whatever like that. But it's only going to cause you problems when you have two things that are not independent of each other, but you're treating them as independent of each other. Okay, so there's that. I'm going to set my y is equal to y naught. So this is equivalent of what I did right here. So I need to pass it that. So here's my function, boom, boom. And I need to end the, when you do the function inline, you have to have an extra end. And I think that's it. So I'm going to come in here. Oops, I need that. So I still need all this stuff. And now I'm going to say y equals Euler of dy dt, t, and y, or this, I'm going to do y. Let's do this, y Euler. There we go. That makes it a little less confusing. So I'm going to plot this against y Euler. And let's run this, see if I screwed up. Yay, I didn't goof up. Okay, so now the nice thing, oh, I changed this. If I do, like if I want to make that really fine, then you can go through and change it. It'll automatically take care of stuff, and boom, we hide the real thing. Okay, but again, we're asked to do, for this problem, we're asked to do 0.25, so we'll go with that. Okay, so there is my Euler's method, and there's my Euler's method function. Okay, we need to add a legend to this, but quite frankly, we're going to keep on adding stuff to it, so I'm going to wait till the end to add the legend. Okay, so then the next one is midpoint function. Okay, so we're going to do boom, midpoint, and we're going to do the same thing. I'm going to come in here, and actually, quite frankly, I'm just going to use on all these, 0.5. I don't want to use 0.5. I'm going to use 0.25. To be fair, the problem says 0.5, but that just is too coarse. So I'm going to use 0.25. So I'm going to use this for all of them. So then I'm going to come, so I don't need to redefine that. I don't need to redefine this. So let's just come in here and actually create the midpoint function. So the midpoint function, y is equal to midpoint of dy dt, t, thanks, well, t comma y, same deal, right? And I'm actually going to cheat, and I'm just going to copy this all down here to start. Okay, and now here's where things are interesting. When all is said and done, this, like all of them, is simply, that is still exactly the same. The midpoint function is just saying your next value is your current value plus your slope times your step size. That's what all of these things are. The difference is how do we calculate slope? And that's where things are interesting. So the midpoint function, the idea is if I know what the slope is in the middle of these 2 points, I'm going to use that as my slope. So I'm going to come in here and I'm going to say slope is equal to dy dt at the, I'm going to call it like this, t mid, y mid, right? So, okay, that's lovely. So the problem is I don't know either these t mids or y mids. And actually this one I do know. What I'm going to do is I'm going to say this is t of I. No, I lied. I'm going to leave it there. So this is not the most efficient way. I'm going to say t mid is what? T of I plus h over 2. Right? So I'm my current time step plus a half a step. So that's my t at my midpoint. Right? So that's where that's coming from. And what is my y at my midpoint? Well, it is simply the, I don't know, right? I have to guess forward. So how do I guess forward? I'm going to say my y at I plus my slope. I'm using the Euler's method, so it's going to call dy dt at t of I comma y of I. That function times my step size, but I'm only going to take a little tiny step, right? So here's the idea. I'm coming in here, and so whereas Euler's method, I go through and I say my slope at this point is whatever it is. I'm going to take a full step forward. Now I have a new point. right? So if I look at the plot, right, I'm looking right here at this point. I'm saying, here's my slope, and I'm going to step all the way to here. And now I have a new point. So here's my new slope. I'm going to step all the way to here and so on. What the idea of the midpoint method is, I'm going to say, hey, if I jump forward just a little bit and say halfway between this point and this point, then that would be my guess of what that point is. If I use that point, what is the slope at that point? And I'm going to use that point to guess. Then I'm going to come back and say, hey, if I knew magically the future slope, which I did, right? I predicted. That's why these are predictor corrector. I predicted the value there. I can come back and I use the slope at that point in the past and say, hey, boom, what is it moving forward? And then we're going to go from there. So that's what we're looking at. Okay, so I'm going to come in here. So I'm going to have my halfway point. My time at my halfway point is my current time, plus a half a step. My predicted guess is my current guess. And this line is just the Euler's method, right? It's my current place plus the slope at my current place times a half step. Now I have a guess at my future point. So then my slope for this whole thing, I say, well, the slope of the whole thing is the dy dt at that midpoint time and that midpoint location. And then I can come back and I figure this out, that therefore this whole thing is like that. Now you could do this all in one line. You could definitely make this more compact as far as code. I really like that it is, I'm trying to be very explicit here. So what I need to do here, I can say y mid is equal to midpoint. I just call it midpoint, right? Y dt, t, and y. So I'm going to do that. I think that should just work. I'm going to plot t comma y mid. I'll do these with a blue O with a dash dot. So we can look at them. Let's run that. Hope that we did it right. See if we made any mistakes. Apparently I made a mistake. Why not? Oh, where did I put why not? Because this needs to be passing a why not. Okay, try again. If that's the only mistake, then yay me, it's actually surprisingly efficient. Boom. Okay, I just realized I made it blue and the initial plot was blue. So instead of blue, let's make this say magenta. So it's just a little clearer which one's which. And look how much more accurate that is. It's mind-blowing. That is so cool. Because again, the difference is with Euler's method, we're starting at this point, and all of our information we know at this point. So we're going to use that slope, and we're going to project all the way to here. Once we're here, we don't know that we have an error. As far as we're concerned, we are where we're supposed to be. And so we're going to say, hey, anything I know out here, I can use that slope all the way to here, and so on. Versus a predictor corrector method saying, hey, I'm here. If I scoot a little bit forward and guess what the slope is, then I can figure that slope and come back here and use that slope to go to there. And now I'm going to scoot a little bit forward, guess what the slope is, come back and use that all the way forward. And it makes it so much more accurate. Okay, so then the next point is Hume's method. So Hume's method. So we're going to do the same thing. And actually, quite frankly, I'm just going to copy and paste this because it's super easy. Boom. But why Hume is Hume I think that's all the same, and we're going to call this y Hume, and we'll do this with boom d boom. I have found if I do the dot dot, I like making the line width bigger so I can see it better, and so we'll do it just a little bit fatter line. I have just found without this line type is hard to see. Okay. So what is the Hume's method? So it's the same idea, but whereas in the midpoint method, we're jumping a half step forward, and then we're going back and using that. Hume's method, we're going to say, hey, what is the slope here, where I am now? What is the slope in the future place where I am? And then take the average of those two, right? So it's going to be the same thing. So I'm going to I'm going to start with the Euler's method again. Boom. Okay. And do Hume, same H, same T, but again, it's the same deal here where it's just simply slope times step size, because again, all of these are the same. My next point is my current point plus my slope times the step size. All three of these are exactly the same. The difference is that how you calculate slope. So in Euler's method, I calculate slope by just evaluating the function at the beginning point. In midpoint, how I calculate slope is I take a half step forward and kind of use that to figure that out. In Hume's method, I'm going to take a full step forward and average the two. So I'm going to do this. I'm going to say slope is equal to the slope future plus slope present divided by 2, the average of the two slopes. Right? Fair enough? So then we need to get into what in the world was slope in the future. So the slope, if I can spell out slope present, that one is just dy dt at t of I comma y of I. So that one's actually nice and simple, right? That's just the calculating it right here. It's the slope of the future that makes it a little more hard, right? Slope future is dy dt of t future comma y future, right? Because that's what they all are. So again, I'm doing this super inefficiently as far as the number of lines of code. You can put this all in like just 1 or 2 lines of code, but I want this to be really clear what I'm doing. Okay, so what is a t of future? T future is simply t of I plus h, right? So I'm making a full step forward, I plus h. Turns out that's also t of I plus 1, right? Because when t is a vector, so the next element of the vector, I don't know, I'm gonna go with that just because that seems reasonable. And so what is my y in the future? Well, this is where we have to guess. Again, we're predicting it, and we're gonna come back and correct it. And so the guessed point in the future is just gonna be, again, Euler's method. So I'm gonna say it's my y of my current y plus my slope, if I, oh, you did it, slope present times step size, right? So again, big picture, this line is just straight Euler's method. My next point is my current point plus the slope at my current location times the step size. So I've already figured that all out, so boom, good to go. So my slope at my current location is just evaluate the function here. My future point is just going to be my t of I plus h, stepping one step forward. So my y, my guess at what the value is at that future point, is just my current point plus the slope times the step size. And then I'm going to say, well, the reason I need to do that is because I need to calculate the slope in the future, and that slope in the future is the function evaluated at time in the future and y in the future, right? And then the reason I need that is because I'm going to say, well, actually, for the real deal, I'm going to use my slope as just the average of the current slope and the future slope. So it's slope future plus slope present divided by 2. And then, boom, you're good to go. Bob's your uncle. You got your stuff. So let's come in here, and let's run that. And hopefully it works. Again, hopefully it didn't make any typos or anything like that. Look at that. So it turns out that line width is too fat and obnoxious. So let's put it as 1.5 so we can see better. Actually, is that an update to MATLAB? Huh. Oh, it made the marker size bigger too. That's interesting. Okay, so there we go. So you'll notice they're not exactly the same, right? But they're pretty darn similar. You can start to see them diverge a little bit here and there. Okay, and then lastly is the fourth order RK method, and I'm just gratuitously cheating and not developing that here. Because again, what is the RK? It's right here. This is straight from the slides and from the book. This is, again, there are infinite number of RK methods. This is thus kind of standard RK method, and it's these weights on here, and they solve for that. So that'll be another video at another time. But let's do here, boom, RK method will be. So y RK is equal to, did I call it big RK or little RK? RK4, okay. RK4 for that, and we're gonna RK, and what are we're down to green with a square, and actually we'll do triangles, and we'll do solid line, if I can hit solid line. And let's come in here, and I'm going to not do this line width because I like the standard line width for most stuff. And we're going to do legend, the symbolic, midpoint. Oh, no, next one's Euler's. Midpoint, unes, and RK4. Run that, and then eventually, yep, there we go. we get this lovely answer. You'll notice that RK is crazy accurate. So it comes way up there, but it's looking pretty good, and we should probably add a title. So title, this is problem 22.1, right? I think, yep, lovely. 22.1, X label is time in seconds, oops. And Y label is Y in, no idea what this is. Actually, do we know what this is? What are we doing? Solve, yep, no, it's just some Y. So I'm gonna own it right there, boom, run that. And we have, come on, you can do it. Where'd you go? There we go. And we have our problem. That's it. Okay, if I can figure out how to stop recording, and we're good to go.